Okay, hi guys. So in this lecture, we'll be continuing on seeing more on the complex reaction, which we saw in the previous lecture, and then we'll be seeing the two methods, which is the RDS method and the steady state approximation method for calculating the rate of reaction. So the reaction was, we had 2 moles of NO2 reacting with F2, forming 2 moles of NO2F, which in step 1, it's a complex reaction. So in step 1 we can write NO2 reacts with 1 moles of F2 at K1 as the rate constant, as K1 as the rate constant, forming NO2F plus F. This is the slow process or a slow step or the RDS step. So then what happens is NO2 again reacts with the formed intermediate at K2 rate constant, forming NO2F. This is the fast process. So our method 1 was RDS method. So in RDS method, we will be taking the rate constant of the first reaction to determine the rate of reaction for the complete complex reaction. So R would be equals to K1 times NO2F, or rather NO2 and F2. So this says that the rate must be dependent upon the rate of the slowest step, which is this one. So method 1 says that rate of the overall reaction would be determined by the rate of slowest step, which is this one. Then we come to method 2. Method 2 is steady state approximation method. In which we can say that rate of reaction would be equals to minus d of F2 upon dt would be equals to K1 times NO2 and F2 okay, and rate of dissociation of NO2 can be written as minus d of NO2 upon dt would be equals to K1 times NO2F2, which is from the first step, and K2 times NO2F, which is from the second step. Okay. And we can also say that d of F upon dt, which is the intermediate, or the differential form of the, or the rate of change of the intermediate, would be equals to K1 times, this is the rate of appearance of this intermediate, which should be equals to K1 times NO2 F2 from the first reaction, and rate of disappearance of the same should be written as K2 times NO2 and F. Okay, and this, according to the steady state approximation method, the change in intermediate's concentration should be equals to 0. So we can write from here that the concentration of F would be K1 times NO2. We are taking from here, so just shifting it to the right hand side of the equation. So it should be K1 NO2 F2 divided by K2 NO2. Okay. So now we can write that. So putting this value in this equation, let's call it equation number 1. So putting the value of F here in equation number 1, so we will be getting minus d of NO2 by dt, which is the rate of disappearance of NO2, can be written as K1 times NO2F F2 plus K2 NO2. What is the value of F here? Value of F can be substituted from here, which is K1 NO2, or rather NO2 and NO2 get cancelled, so no need to write NO2 here. we can directly write F2 here divided by K2. So K2 and K2 get cancelled out. So what would be remaining is K1 NO2 F2 and K1 NO2 F2. So we can write it is twice K1 NO2 F2. And if we look at the original reaction, it was twice NO2 plus F2 giving 2 moles of NO2F. Okay, so if we take 2 on this side or on the left hand side, it is half d of NO2 upon dt, and this quantity is nothing but the rate of reaction, which is nothing but the rate of disappearance of NO2 divided by the stoichiometric coefficient, which is 2 in this case. Hence this would be nothing but the rate of reaction, that would be equals to K1 times NO2 and F2. Again we got the same result as the result we got from the RDS method, that the rate is equivalent to the rate of the slowest step. Okay, now let us see another example. We have 2 moles of NO reacting with O2 forming 2 moles of NO2. This can be further classified into 2 steps. Step 1 has NO reacting with NO for in the KF, it is forming N2O2, and this is a rapid reversible step, and this is the KB, obviously rapid reversible step. And the second step is the form N2O2 again reacts with O2, or rather now reacts with O2 at K2 to form 2 moles of NO2. This is a slow process. Okay, and we are taking some assumption here. That reversible step is in equilibrium, and we can write that Kf times NO to the power 2 would be equals to Kb times N2O2. This simply means the rate of forward direction is equals to the rate of backward direction. Rate of forward direction would be Kf times the reactant of forward direction, which is NO, and as this is a elementary step, we are putting the value 2 here, which is the stoichiometric coefficient in the power, and this should be equals to rate of backward direction. Rate of backward direction would be Kb, which is the rate constant of the backward direction here, not here, these 2 moles, yes, and Kb times N2O2. N2O2 is the reactant for the backward direction, hence for rate of forward direction would be equals to rate of backward direction. Okay, so let's apply RDS method on it. So according to RDS method, we can say that rate of reaction is equals to rate of RDS step or rate determining step. Hence rate would be equals to K2, as this is the slow reaction, so rate would be equals to K2 times N2O2 into O2, which is the nothing but concentration of N2O2 into concentration of O2. Concentration of N2O2 times concentration of O2. So this is the rate of reaction. Okay, and we also know that N2O2 is an intermediate product, so we need some work around that to convert N2O2 in this reaction with other reactants which are actually present into the as the initial reactants of the reaction. So we know that rate is equals to K2 times. Now for N2O2 we can substitute the value of N2O2 from here, which would be Kf NO whole square divided by Kb. So it would be Kf NO whole square divided by Kb. This is the value of N2O2 multiplied with O2. Okay, so this would bring us Kf K2 divided by Kb NO whole square and O2. So this would be the rate of reaction. So now we can write R equals to K times NO squared O2, where K is equals to K net, or only the rate constant would be equals to Kf times K2 divided by Kb. This would be the rate constant. This is nothing but the rate constant for rate constant of complex reaction. So with this we come to the end of this lecture. In the next lecture we'll be seeing more on the rate constants, and we would also be deriving the relationship between K, Kf, Kb, K2, and we'll be seeing that with Arrhenius equations. So till then, good luck and goodbye.